Okay, thanks, Sybil. And hi, everyone. So I'm presenting this work. It's a joint work with my advisor, Moshe. And it discussed long-term data sharing under exclusivity attacks. So soon we will know what this means. Okay, so I'll begin with a simple use case of what we are discussing. So let's say we have two real estate marketplaces. In Israel, we have, for example, Yad2 and Madlan. And they want to build some model that will help their users to predict house prices. So every user that already sold an apartment or buy an apartment can report the square meters and the price that it was sold. And they want to run some linear regression and see the model predicted. Now, they can each do it by themselves according to the data that they accumulated, but they can also share the data that each of them collected and build a model that is a shared model between them. And hopefully, because it contains more samples and because maybe they see different aspects of the full spectrum of the users, then this shared model will be better. So this is ideally they would share. Okay, and in this type of problem, there is a growing interest in many directions. There are cloud services built for people to share their data with each other, for companies to share data. There are government initiatives to do so, especially in the European Union. And also there are blockchain platforms to do that. But obviously, there are some strategic aspects to this problem. So the strategic aspect that we are focusing on is what firms want to do. They want to see the best model fit that is possible, but they have a secondary goal, which is to mislead the others. They can get some competitive advantage if they are able to mislead other firms, but their main goal is to get the best model fit. Okay, and this is a bit different from privacy and also a bit different from poisoning. Sometimes it's considered like poisoning the model, but in this case, you don't want to poison the model. You want to still be able to infer the best model, but you want the others to have a somehow degraded model. Okay, so let's see a simple example for this in the one-shot case. We are going to be focused on the long-term case, which is users keep updating and the models keep building and progressing. But let's see an example from the one-shot case. So let's take the algorithm sum. Let's say the two firms want to see the sum of the numbers they have. So one agent has 10, the other agent share it as it is, the sum is 30, they both know 30. There is a manipulation possible. And shift the number it sends, then it can later reduce it from the sum that they get, and they know the number 30, but the other agent got some wrong number. Okay. All right, but this doesn't work for every algorithm. There are algorithms where it doesn't work. So let's see an algorithm it doesn't work. So let's see the algorithm max. One agent has the number 10, another agent has the number 20. So the maximum is 20. Okay, so one agent maybe wants to manipulate this. Instead of 10, it sends 25. Okay, so it was successful in manipulating. The other agent got the wrong number. But does this agent know the true max? I mean, it cannot tell the difference whether agent 2 has, for example, 15, 20, or 25, based on this number 25, because no matter which of these options the other agent has, the maximum of the algorithm, the algorithm output would still be 25. Okay, is this clear? Okay. So let's see what change. So this is known, basically. Maybe not these specific algorithms, but this is known from prior work. What changes when we move to the long-term model? So first of all, long-term cooperation has some opening for Sybil attacks, because what we see here is that they have one update to send, and they get one algorithm output. What can happen when you have long-term cooperation, maybe an attacker can send multiple updates, and in this way query the system, get more results, has more information about the true model, and it allows him to have better inference about this model. Even though it's not, it's sending wrong results, but many of them, and get more information for this model. So a simple example for this is that there is a paper that shows that you cannot infer average by sending a wrong update. But what we show, it's not too complicated to show that if you have two updates that you can send and see the average after each one of them, then you are able to know the true average, even though you sent wrong data.
Yotam, I'm a bit confused. What exactly do I see? Do I see the report of everybody else? Do I just see the average?
No. You don't have visibility to the report of everyone else. You just have some, let's say you have some central authority. Everyone sends this, I will define the formal model soon, but everyone sends this, their updates to this authority, and the authority each time publishes the result of the algorithm or the model.
Okay, so for the average, if I know how many numbers we're averaging, then and I know how I miss.
Yeah, if you know.
Sorry?
Yeah, exactly. It depends on that you know the number, but in a real situation, you don't necessarily know. Let's say that the format of the updating is you just send points. So you don't know how many points the others on the other side sent.
I see. Thanks.
Yeah, so that's actually really the missing information, the number. But with two samples, you are able to deduce it, to infer it. Okay, but a safety benefit that we have if we have long-term cooperation is that the attacker cannot perform an attack and corrupt the mechanism in a way that would prohibit it from inferring future. So they don't want to really poison the mechanism in a way that in the future would not be able to infer the true model. Okay. So so now I will move to a more formal discussion soon. So I'm going to define what is a continuous model of communication. We see two ways to define vulnerability for this. Basically, vulnerability will mean for us that sharing data truthfully is not an equilibrium. And then we look at the example using linear regression and clustering algorithm K-center. And later we see that if we somehow change the model of communication, then the results can change. Okay, so far? Okay, so let's go into the formal model. So we have n agents, and we have three main entities here. We have the nature, we have agents, and we have the ledger. Nature represents reality, like the agents get true information about the world that they know from their users or from their data, and it keeps updating. Okay, so we have nature sending factual messages to the agents. We have the agents. The agents communicate with the ledger. Ledger is the central authority here. So agents can send updates to the ledger. the ledger cannot see what nature sends, but it can see what the agents update. And after each update by an agent, the ledger shares the most updated model or the result of the algorithm based on all prior input that it accumulated. Okay, so let's see an example of this. This is like the code. I'm not going to go over the code for real, but let's see an example of run with max. Okay, and in this example, we have agent 2, which is truthful. We have agent 1, who is going to be manipulative. And let's see this example. Okay, so nature updates agent 2 with the number 90. Okay, so agent 2 now knows 90. Because it's truthful, it shares 90 with the ledger. The ledger only has one number, 90, so it's the maximum. It shares it with both agents. Okay, now agent 1, according to his strategy, when she sees 90, she sends X. And X is higher than 90. So the ledger looks at 90 and X and shares X with both agents. The next move, so after this, nobody responds, and some time passes. Nature updates with Y to agent 2. Agent 2 reports it truthfully. Now we say that Y is lower than X. So so the ledger sticks with the number X and shares X with both agents. So what went well for the attacker here and what went wrong? So what went well is that it managed to mislead the other agent. For example, at this stage, it's thought that the algorithm output is X, even though it was supposed to be 90. What went wrong? Actually, the same that happened in the one-shot case happened here. Y, let's say X is, I don't know, 200. Y can be 100, 110, whatever, and Y should be the maximum after this stage. But agent 1 cannot tell what is Y. I mean, the observed history for agent 1 would look the same under any Y that satisfies these inequalities. Okay. So let's define what I said in general. So each agent has its own observed history. They don't have a way to see what the other agents have or what they send to the ledger, but they are able to see their own factual updates. They are able to see what they send to the ledger, and they're able to see the algorithm outputs. Okay, and the strategy would be a mapping from these observed histories to ledger updates. So if an agent sees, for example, agent 1 sees 90 here, and this is the only thing he sees, then he sends this ledger update, this number X. So the strategy is the decision tree based on the observed history. And the strategy,
Yotam, can I ask a question?
Strategy is simply, yeah, sure.
Did you say that the main objective of every agent is to learn the truth, and then the secondary objective is to mislead the other agent?
Yes, exactly.
Okay, agent 1 here knows that there is one more player, that there is one more agent?
Yeah, they know the number of agents.
So, for example, when agent 1 gets an update of 90, he knows for sure that agent 2 sent 90 to the ledger?
Right, so here there is also a privacy issue, I agree, because it's only 2 agents. Yeah, but let's say there were 5 agents, then he would only know, that there was an update that changed to 90.
No, but my question is, if at this point agent 1 knows, if agent 2 is truthful, and agent 1 knows at this point that agent 2 sent 90 to the ledger, then he doesn't really care about the output, and we don't have a problem. He learns everything at this stage, and then he can say 1 million, mislead agent 2, and he already knows the truth. It doesn't matter that the output would be X.
This would work in the one-shot case if it was like I don't know, like a sequential game in the one-shot case, and and this agent is the last to respond, and he has this advantage. But we want, I will get into the definition of vulnerability soon, but the agent wants for any type of nature input to be able to infer the true model parameters or the true algorithm output. And in this case, we see that if the agent follows this strategy, that it updates with 1 million after 90, then if nature would later update the agent 2 with Y, then agent 1 will be in a conundrum, like it cannot infer Y.
Oh, okay.
Does this answer the question?
So I guess the question might be whether the agent is going just to use the model output by the ledger, or he can use anything he can infer from his own.
Agent 1 can do, right, the strategic agent can do anything with the output, doesn't have to use. The truthful agents use the output, but the strategic agent can do anything.
Okay. Thanks.
Okay, so let's see the vulnerability definitions. So we have like a weak vulnerability and a strong vulnerability. Let's start with the vulnerability. So we would say that that the protocol bundled with the algorithm are vulnerable if the agent has such strategy that there is some nature input, so that the last algorithm is different from when running between this strategy, this manipulation, and the truth. This means there is some case, there is some state of the world that the agent is able to mislead the others. But also we have condition 2, that if we have two nature inputs that are different under the truth, we want to see that they are different also under the strategy. Okay, so this implication is that it also implies that there is some inference function that based on the observed history under the strategy, we are able to map it to a true state, to a true observed history in one way. Okay, and the additional condition for strong vulnerability is that actually for every nature input, the agent is able to mislead the other agents. So yeah, so this is stronger in the sense that it's more successful in misleading others. Okay, so if this is clear, I move to start talking about the specific algorithms. So we have linear regression. I think this should be pretty familiar. We have some D features, and we want to extract a prediction for the some dependent variable. Okay, and we're using this optimization problem and this formula. Okay, so let's see a strategy that proves that that linear regression is vulnerable. If we happen to have, if we as an agent see this line, the blue line, and we also see a factual update that are the X points, okay? And it happens to be that this line and the line determined by the points that we have is actually the same line. So what can we do? I mean, for sure we know that if we send these points to the algorithm and we and we would get the new optimized line, then we would have actually the same line, because this is optimal both for the data we have and for the data, for the general data. So what the manipulation we can do is maybe we send only the some part of the points. It would cause the red line, the upper line, or never mind, or the lower points, it would cause the lower line. And then we are able to mislead the others. And when we see another output coming from the algorithm, we know some other agent made an update, then we complete the missing data, because in this case, maybe we don't know for sure what happens later. So this is like for one stage of this run, we are able to mislead the others, and then we move it back. Okay. And this can be used as a general template. So the general template here is we see some algorithm output, we see a matching factual update. It doesn't have to, I mean, the example of linear regression here was they are exactly matching, but have to be have this condition. We will see in case center that a different example than this, and then you send some wrong data, and later you maybe resynchronize the ledger with what is true. Okay, and so sneak attacks are actually enough to show that truthfulness is not an ex post equilibrium according to how we defined it. What does it mean? I mean, it means that there is, so ex post equilibrium means that after the draw of some nature input, the agent would always want to be truthful, even knowing the nature input that was drawn. In this case, it wouldn't be true because it would prefer to move to this sneak attack. But maybe it's not enough to disprove Bayesian-Nash equilibrium, because maybe it only, I mean, this example is maybe very low probability that actually the sample you get and the sample that the system at large got by the time that you get this input are the same. I mean, it's quite a low chance. So it's enough for export. Maybe it's not enough for Bayesian-Nash. So now we move to vulnerability star. The thing is, vulnerability star, because it shows for every nature input, then no matter what is the measure that we define, it should be enough to show that the truthfulness is not an equilibrium.
Yotam?
Okay, so let's see what we can do. Yeah.
Can you go back one slide, please?
Sure.
Oops, I think it got stuck for me. Okay, thank you. I'm a bit confused with your solution concepts. I do not quite understand what's ex post equilibrium in your model and what's Bayesian-Nash equilibrium in the model, in your model. What's Bayesian here?
Okay, so actually, right.
And also you define the multi-stage. Oops, I think there is some delay, so I apologize for this. You defined a multi-stage game, so that confuses me even more.
No. Wait,
with respect to.
First of, okay, so first of all, we don't define it as a multi-stage game because the strategies are actually they are function from every observed history to ledger updates, so they don't have some temporal aspect to them. It's not it's like it's a normal form game just with these strategies. So that's one thing. And okay, so the discussion about equilibrium, actually I do it a bit informally, because we gave a condition which is like a logical it's like a logical formula. We don't actually define the utilities and the game. But if you were to define this as the utility is as we said, lexicographically, you want the best model, and then the second thing you want is to mislead others. Then in this game, and you would have some measure over the possible nature inputs, again, which we don't consider some specific measure.
But you know the underlying distribution of the nature input?
No, so this slide is, we don't discuss anything that has to do with distributions. But if someone would have,
what do you mean by Bayesian Nash equilibrium here?
Okay, so if you would complement this model with a measure over the nature inputs, okay, and then you could consider things like the ex post equilibrium or Bayesian Nash equilibrium given this measure, some measure, okay? And what I'm saying is that if you follow this condition, you would see that in an ex post equilibrium, you need for every nature input that deviating to manipulation wouldn't be better than the truthful strategy. So if we show that there is a nature input that the manipulation is better than truthful strategy, it shows there is no ex post truthful equilibrium.
And you assume that other agents are truthful, I guess, in
right.
an ex post.
We look at the truthful equilibrium.
Okay, so I understand. Okay. I understand ex post equilibrium then, but
okay, so
I mean, if it's not important that we understand Bayesian, it's fine. But I don't understand it yet.
No, I think it's good to understand it maybe. So for the Bayesian Nash, you would want so Bayesian Nash. If there is something of measure 0, some event of measure 0, and it wouldn't get calculated into the expectations, and then maybe truthfulness would still be an equilibrium, even though there are some measure 0 cases where it's less good than the manipulation.
Okay, I think we should go on.
Yeah, okay. Okay, so anyway, what we show now is that you can actually, given enough updates for the agent, then it can actually satisfy vulnerability star. So actually can always mislead the others and also infer the true model. So the structure of this triangulation attack is the agent sends an update, gets some output, then based on this output sends another update and so on. And using all these updates, gets enough information to infer the true model parameters. And maybe at the end, send some last update that would mislead the others. Okay, so this is based on having enough updates. And what we show is that if we have around the number of updates as the dimension of the linear regression problem, the number of features, then we're actually able to do that. So what is this based on? So this is based basically on the expression for the linear regression optimal solution. We are able to separate it to what the others update and what own agent updates. So it is enough to infer these matrices, this matrix and this vector, in order to know what will be the solution given anything that you as an agent would send. So these are like D+1 over D+1 matrix and D+1 over 1 vector. And you get equations every time you get equations over this every time you send an update. Now the only problem with doing that is that when you when you get new equations,
Can I jump in?
Yeah.
I lost you for a second. Can you repeat what exactly are you proving? What are you counting? What's the claim?
Okay, so the claim is that linear regression is vulnerable star, as we defined it, given that we have enough updates. So we have a parameter that limits the number of updates that an agent can send. Okay, so this is actually a good point. Each agent, so you would assume that maybe the ledger wouldn't want this type of attacks to occur, so it would limit the agent from updating too many times with one after the other. For example, if you acquire some data, you send it, but you cannot send again and again and again, one after the other.
So when I'm sending just one point or many points?
You can send many points. The question is how many updates, like interactions with the ledger you have.
Okay, and you are
after each interaction, the ledger is going to respond with an algorithm output.
And you are claiming that if I have very few updates, I will not be able to manipulate, but if I have many, I can do that. And what's many? What is D?
D is the number of features of the of linear regression. So if it's a simple linear regression, D would be 1. If it's over 100 features, it would be 100.
I see. Thank you.
Okay. Okay, so the only thing that you need to consider is how to make sure that the equations don't actually add new information every time. And for this, we give some construction. So I just want to show how it looks. So if you would have sent the truth, here you have the other agents have the red points, and you have the orange points. So if you just want to get the true information, you would send the orange points and you would get this line. But the alternative using triangulation attack is, first of all, you observe how the algorithm output looks after you did not send any update, or only based on your prior updates. And then you send this type of sample updates that are meant to get some information from the system, and based on all of these lines, you are able to infer what's on the line on the left side, and also you were able to mislead, because this line is the final line at the end is not the same line as the left. Okay, so now I will move to case center.
Yotam, can you explain again the last slide? I somehow couldn't.
Okay, so this is just from a script.
Who is you? You are the orange guy here?
Yeah,
you have the orange
you are the
points.
manipulative agent that is going to maybe try a triangulation attack.
Okay.
And so this is from some script we have that simulates the triangulation attack. So
what do you see and what are your points?
Right, so you only see lines. Sorry, you see lines and you see your own data. So in this case, you don't see the red points. You see the red line, and you see the orange points that are your own data. Okay, and if you manipulate, then you see first you see the line, the red line. Then you send the blue point. You see
so how do you manipulate? What do you do in this manipulation?
So you follow the construction of the construction that we give the triangulation attack, but basically you send some point that needs to satisfy some things, so that that it would give you enough info, that it would change the line in a way that would give you an independent equation of
okay, but I guess what my question is about the graph in the middle. The graph in the middle is before you
so
send
actually all three graphs on the right are part of the data that you will use in the triangulation attack. So the first, you mean the middle graph? right?
The middle graph, what are the red points here and what is the
red points are the points that the other agents shared with the ledger.
So how come it's different than the one on the left?
It's just the scale. I think it's just the scale of the. Yeah, I'm sorry, I didn't scale the.
It's the same points. Okay.
Yeah, so it's the same points in all of this. It's just the graphs are scaled again. But
okay.
So these are the points by the other agents, then you have the line. So okay.
Okay.
Can I ask?
Okay, so let's
can I also ask a question, Yotam?
Yeah, sure.
So do you assume that like the one who is doing kind of the attack is doing them one after another and there are no updates in between? Or
right,
like...
yes, you do assume that. The reason we assume that is, I mean, first of all, it is possible. I mean, once you know, if you're a strategic agent and you know you want to do a manipulation, you can send your updates very fast after one another, or maybe you know something about the other agents that they only update daily or something like this, you update a few times in the same day. So yeah, in this model, in the continuous model, we have the agents have the opportunity to update several times in a continuous way.
Okay.
It's important because once some other agent updates, this can change. I mean, this kind of resets the picture.
Yeah, exactly. So in a sense, this is why you can do stuff in kind of the multiple steps game when it's more similar to one-shot.
Another thing that is important to emphasize. Another thing important to emphasize is that consider like Sybil attacks. So for us, the reason that you cannot limit this type of attacks is even if you block each user not to update subsequently more than one time, then it would be able to maybe control other entities or have some sock puppets that would update later. I mean, update subsequently to itself. And then you would still have this ability. So you cannot really block this ability from Ledger. Yeah. Unless you know there is some limit to the number of fake entities. If you know that each of the agents can at most control one entity, then your limit is one. Yeah, but we don't make this assumption. We keep it open.
Yeah, I guess also if you know that usually there are, I don't know, like 5 updates per hour, and now suddenly you get 20, then you know someone is doing something wrong.
Yeah, so this would establish some limit, but we keep it open. Like yeah, exactly.
Okay.
Yotam, another question. So Yotam, I understood that in the upper of the two right, you basically put some point that will give you some independent equation that will allow the attacker to retrieve the truth, right?
Yes.
And then what's the goal of the lower, the lower of the two right graphs? Why should I add another point?
Yeah, it needs another equation. So actually, so if the theta of d is actually d plus 2. So in this case, it's a simple linear regression, so you need 3. But yeah, so
I see. Thanks.
Okay. So let's move to K-center. Okay, so just to define it, I'm not sure everyone is familiar with it. So it's a facility location problem. You need to find K centers among the points that you have that can serve as like service centers. And your goal is every point is going to be attributed to a center, and you want to minimize the maximum distance between a point and its center. Okay, that makes sense. I mean, in this example, -2 and 6 are going to be the result of K center, and the cost is going to be 2. Okay. Now, first of all, we see that sneak attacks can also work for K center. So let's consider that as an agent, you see the output -epsilon, 0, and epsilon. So this allows you to know that these points exist. It doesn't mean that these are the only points that exist, but they were chosen as centers. And what we say is that in this case, if you see the factual update 1, 2, 10, and 100, then you know with certainty that the algorithm output after you send it is going to be 1, 10, and 100, no matter what are the underlying, I mean, it matters what are the underlying points by the other agents, but because you saw, oh wow, my battery is going to run out. I'm taking a 5 seconds break. Okay, sorry for the disruption. Okay, so we don't know the underlying points by the other agents, but we know that this was chosen as the outputs. So in this case, you can show that the algorithm output is anyway going to be 1, 10, and 100. But if you send only the point 1, then it's possible. I mean, condition 1 is satisfied in the sense that it's possible that there will be some other algorithm output than the one that it's supposed to be. Okay, and then in the next step, we can resync the ledger with the truth. Okay. On the other hand, for K-center, we can show that it's not a vulnerable star. So why is that? So the first step to show that is to show that a vulnerable star requires explicit lies. So we make a distinction between explicit lies and omissions. So omission would be something similar to what we did just now in the sneak attack. You have some points and you don't report all the points. You only report a subset of the points. But there is no, you never report a point that you don't have. Explicit lie would be to report a point that you actually don't have. Okay, and vulnerable star requires this explicit lies because, for example, there can be some nature input where you actually don't have any points. You might have some agent that joins this ledger, but actually doesn't have any real data. It's only there to manipulate. Okay, so vulnerable star requires this, and now we're going to show that in the case of K-center, explicit lies are going to contradict condition 2. Okay, so we show it for a larger class than K-center. So first of all, notice that K-center is something we call a set choice algorithm. So it returns as output some subset of its input. And it has a property, you can show it has a property that we call forceable winners, which means that if you have some set and the point in this set with some other set, so that this point would have to be chosen as a winner. In our case, winners are centers. Okay, so in general, why would set choice algorithm with forceable not be able to explicitly lie without contradiction condition 2? Okay, so it's an explicitly lying strategy. So there is some point X, which is not part of the data, that it reports sometime. And the true factual data is some S, and we know X is not part of this S. So now we can use this bar S. Let's say that at the next step, some truthful agent gets bar S and reports it and updates with this bar S. So what will we see under truth J? So okay, so actually, sorry. So there are two possible inputs that this other bar S or X and bar S. Okay. So under truthful, we will either have S minus X with bar S, or we would also have the point S, we would have S with bar S. By possible winners, we have that X is part of the algorithm output for S with bar S. But because it's a set choice algorithm, and here X is not part of the input, then X would not be chosen as a center, and the algorithm output would look different. Okay, this is under the truthful strategy. What happens under SJ is because X is already part of what the ledger has, let's call it S tag, then after updating with either bar S or bar S and X, the ledger is going to see the same set, the same input. So the algorithm output is going to be the same. And actually, no matter what the agent would subsequently do, it would still stay the same input that the ledger sees. So it's going to be the same algorithm outputs, and the observed history for the agent is going to be the same. So the agent would not be able to infer what happens under truth. Okay, this is it for the continuous protocol. Now we move to a different protocol, which is going to be done in rounds. So instead of giving everyone the option to update at will whenever they have some update, the ledger sorts of initiates the updates, and there are like daily updates or weekly updates or whatever. And in this case, so we can see the maximum example again. So in the first round, nature updates agent 1 with 80 and agent 2 with 90. Each of them updates the ledger with it, and after the ledger gets the updates of this round, it sends the algorithm output to everyone. So the main change is that the ledger update it updates, but only at the end of a round. Okay. Okay, and all of the results that we saw so far actually change under this periodic model. So that's why linear regression is not even vulnerable under the periodic model. Okay, so it's a similar argument a bit to what we showed for set choice algorithms with forceable domains. We start from a case where condition 1 is satisfied, and we show that it contradicts condition 2. So there is some nature input that is different between this manipulation and the truth. Okay, so in this case, the red line is the true line, and the blue line is the manipulation line. So the lines are different because the agent sent different points. Okay, so in the manipulative case, let's say it sent a tag. So what happens if for some very large lambda in the graphs, its lambda is going to be 3? What happens if at the same round then all of this happened, some other agent updated with the same set lambda times? So So under the strategy, the manipulation, it actually doesn't matter because it's a duplication of the same points, and the line is going to stay the same. It's still the optimal line. But in the case of the in the truthful case, adding all these points that have a different optimal line is going to shift the line. So this means that for the manipulator, it sees this manipulated line. It doesn't know what happened with the other agents at that time, and maybe there can be different model outputs that can match this line that it observes under the strategy. So this argument works for many of the multi-set algorithms like linear regression. This specific argument wouldn't work for K-center and K-median also because they are set algorithms. So this would actually not change the truthful. This wouldn't change, but there is a different algorithm for this. So to summarize of this, so we look at the two protocols for the long-term communication. We define what is a weak vulnerability and a strong vulnerability, and we show the results for the continuous protocol that K-center and linear regression are one NCC vulnerable in the sense that it's enough to have one update. It's enough to have one update to satisfy vulnerability. For K-center, it is not vulnerable star. For linear regression, you need about the number of samples to show a vulnerability star. And this doesn't hold for the periodic protocol. Okay, so I think I still have enough a little bit time to talk about the future directions. Any questions up to now? Okay, so I will mention a few points that I think can be interesting for future directions. First of all, we presented two protocols, and also there is the one-shot protocol. You can try to establish some hierarchy between them. I mean, it seems that the periodic protocol is much more safe than the continuous protocol. But the question is, can you maybe prove it formally that given a strategy that works in the periodic protocol, you would also have a strategy in the continuous protocol, something like that, or from the one-shot? And there are some caveats to it, but maybe it can be shown to some specific cases, or something like that. Another thing that can be interesting is we consider the truthful equilibrium, and for us, the protocol coupled with the algorithm are not safe once you don't have a truthful equilibrium. But maybe someone would be interested, to still know what happens when this happens, like what kind of equilibrium can be achieved. There is also the issue of implementing the central authority. So for our model, the central authority is just some ledger that you send the information to. So obviously this is not very private towards this authority, but it should be possible to implement it in some decentralized way. Okay, and the two things I want to focus about, one of them is there could be different heterogeneous interest between the agents. So some agents use the model parameters in a weekly fashion, and some use it in a monthly fashion or something like that. And this would mean that not all agents care about all algorithm outputs. So maybe one agent only looks at the algorithm outputs once every few once in a while, and the other looks when this happens. Another thing that is interesting is, okay, so here our attacker had really high goals. It wanted to know exactly the correct model, and it couldn't tolerate any move of this model, even by a small shift. And so this is very high expectation from the attacker, and when it works, it's good. I mean, we show some attacks that are actually able to achieve this. But if it doesn't work, maybe the attacker would be willing to take the small lose, and as long as it's able to really mislead the others by much more. So you can relax a bit this demand from the attacker, and when you do that, when the agents are able to suffer a bit of this loss, then maybe you can also introduce approximate mechanisms that would maybe have better safety guarantees than the original algorithm. Yeah, that's more or less it, I think.